just as a quick recap here, let's talk about Kw, Ka, and Kb. So remember, right, Kw is the constant for water. That was 1 times 10 to the negative 14. And then we also talked about what Ka and Kb signify and kind of what those values mean. So remember, if we said Ka is around 1 or bigger, and same thing with Kb, then those are going to be our strong acid and bases. Strong acid, base. Similarly, if Ka and Kb are smaller than 1, and extremely small, that's the total 2 arrows there, we're going to say that's a weak acid and weak base. So in this video, we're going to talk about kind of the reactions between acids and bases, with a particular focus on strong acids, strong bases, as well as weak acids and weak bases. Okay, so let's talk about strong acid, strong base reaction. So let's start with a very typical strong acid, strong base reaction. HCl plus NaOH gives us water and NaCl. Let me just center this on the screen here. Okay. What we see here is that our products are water and salt. And that's always going to be the case. It will always be the case. So always will create H2O and a salt when strong acids and strong bases are combined. So when strong acids and bases combine. So a problem might ask you, let's move down a little bit here. A problem might ask you, what happens when HCl plus NaOH combine to create water and salt? Well, what would the pH be? And so what we'd have to do here is first figure out the limiting reagent and go from there. So let's say I have a 1 molar solution of an HCl with 1 liter. Let's also say I have a let's say 1 molar solution of NaOH, but 0.05 liters. So I want you to pause the video here and see if we can figure out what the limiting reagent or limiting reactant would be here, and how we could go about getting the pH once we have that information. Okay, so let's start with first converting between molarity and moles. So we know that molarity is equal to moles over liter. We can arrange this to be molarity times liter equals moles. And you see here we have everything already here, so we can plug in, right? So for HCl, we can say 0.1 times 0.1. For NaOH, we can say 0.1 times 0.05. We'll get here 0.01, and here we get 0.005. Just by that, we can tell, hey, NaOH is a limiting reagent. But to kind of be more specific here, right, if you wanted to work out fully, we would have to convert between the moles of NaOH and moles of HCl using our mole ratio. In that case, that would be 1 to 1. And so all we would do now is say 0.01 minus 0.005. That's going to give us the remaining moles of HCl. That should be 0.005. Let me scroll down a little bit here. Okay, so then how do we get the pH? Now that's the biggest question here. How do we get pH? Right, if we have 0.005 moles of HCl, how do we get our pH? Well, if you remember, the definition of our strong acid or strong base is that it completely ionizes, which means that 0.005 moles of HCl becomes 0.005 moles of H plus and Cl minus. So we can also say then that we have 0.005 moles of H plus. Now all I have to do to get pH is use the formula that negative log of the concentration of H plus is equal to pH. So now I have to convert between moles and concentration, or molarity. So we know we have to convert our moles here into molarity. But what's our volume of our solution? Would we use 0.1 here? Or would we use 0.05? What would we use here? Well, we'd actually combine them. So we would say that the final, or the total liters here is 0.1 plus 0.05. That would give us molarity. So we would do 0.005 divided by 1 plus 0.05. That would give us a molarity of 0.0333. So now we just take the negative log of that. So negative log 0.033 equals 1.477. So that's how we would solve for strong acid, strong base problems. But let's do another example here where we have more base than acid. So let's use the same formula we had above. Let's use that HCl plus NaOH yields water plus NaCl. But let's this time say that we have 0.5 molar solution of NaOH. Let's say we have 0.1 liters. And for HCl, let's say we have 0.2 molar and again a 0.1 liter solution of both of them. So pause the video and see if you can figure out how to get pH. Okay, so hopefully you got the pH. If not, though, we're going to work through this and see what we can do. Okay, so again, it's the first same step. Get the moles and see what our limiting reagent is. Right, so for HCl, we would say 0.2 times 0.1. And for NaOH, we would say 0.5 times 0.1. Then for moles of HCl, we would say 0.02. NaCl would say 0.05. So again, same thing here. We want to convert either HCl or NaOH to the other one. So we can say that for HCl here, we can say, hey, this means that we need to react with 0.02 moles of NaOH. And you see we have way more than that, which means here that HCl is a limiting reagent. So we can say that 0.05 minus 0.02 will get us the remaining NaOH in our solution. That's 0.03 moles of NaOH remaining. And again, a strong acid definition means that we will completely ionize 100%, which means that 0.03 moles of NaOH would yield us 0.03 moles of Na plus and 0.03 moles of OH minus. So we can say we have 0.03 moles of OH minus. So the tricky thing is, how do we get pH? We have OH minus. So there's two ways to go about this. We can either A, use the fact that 14 minus POH would give us pH, or we can use our Kw expression and say that Kw is equal to the concentration of OH minus times H plus, and we can solve for that way, and then after we would do our pH calculation. All right, so first way, we would have to get POH first, and then calculate pH. The second way, we would get a concentration of H plus first, and then calculate pH. Both ways are 2 steps. Both ways are completely fine to do, and I'll show you how they work out. So it's up to you to determine which way is easiest for you, or maybe easiest from the problem. Okay, so let's do the first way in green. So we want to get POH first. So we know POH is a negative log of our concentration. And again, we don't have concentration yet. So we need to convert our 0.03 moles into molarity. And similarly to the problem we did above, we need to add up the liters to get what our new volume is. So we would take the negative log then of 0.03 divided by 0.1 plus 0.1. And if we're to solve that here, we get our POH is equal to 0.823, which means then 14 minus that. So 14 minus 0.823 is equal to a pH of 13.177. So that's how we would do it the first way. So let's now do it the second way. Okay, now do that one in pink. So we know Kw is 1 times 10 to the negative 14. That has to equal to our concentration of OH minus, which is going to be 0.03 divided by 0.1 plus 0.1 times H plus. Again, we can rearrange this formula here to get that 1 times 10 to the negative 14 divided by 0.03 over 0.2. I just simplified our concentration of OH minus there. That's going to be equal to H plus. That's going to equal 6.6 times 10 to the negative 14. We'll negative log that value to get 13.17. So we see here that we get the same answer both ways. And again, it's completely up to you which way you find the easiest. Okay, so let's now move on to the other type of problem we can get, which is calculating Ka and Kb for a reaction. Let's say with this reaction, let's say we have acetic acid, which is CH3CO2H. We're combining it with water, and this one is in equilibrium with H3O plus CH3CO2 minus. Now, how would we go about calculating the Ka value for this problem? Well, first we need some values. So let's assume that we have 0.0787 molar solution here, and we have 0.00118 of both of our products. So now how do we get Ka and Kb? And remember, Ka has to be equilibrium. So let's assume these values are equilibrium. So let's say these three values here at EQ. That's our equilibrium. So we know that Ka is our equilibrium constant, right? So equilibrium expression. We know that it has to be products over reactants. In this case here, right, if we were to work this out, we would say that Ka has to be equal to our concentration of H3O plus times CH3CO2, don't forget the minus there, all over H3CO2H, you got acetic acid, and water. If you remember, waters are pure liquid though, right? And we don't include pure liquids. So water can go out. So our Ka expression then would just be concentration of H3O plus times CH3CO2 minus all over CH3CO2H. And again, if we assume the values I gave are equilibrium, we'll just have to plug it in and solve. So then we plug it in and solve, then what we should get here is 0.00118 times 0.00118 all over 0.0787 equals 1.77 times 10 to the negative 5. So let's try another example. So let's say now I have this reaction. I have HPO4 2 minus plus water. That's in equilibrium with H2PO4 minus plus OH minus. So for this one, see if you can figure out what our Ka value is if I give you that our concentration of PO4 2 minus is 0.341 and our H2 PO4 minus is 0.092 and our OH minus is 1.3 times 10 to the negative 6. And again here we're looking for what Ka is. So see if you can figure out how we would get Ka value, and again, all of these values that I gave you are at equilibrium. Okay, so we've sort of seen here that this reaction here is actually for a base, right? If we look at it here, from H to PO, from HPO4 2 minus to H2 PO4 minus, we gained H plus. So we're actually here, if we solve for it, we get Kb. And so again, Kb in expression is found the same way. It's our products of reactants with water not counting, So Kb is equal to our concentration of H2PO4 minus times our OH minus all over concentration of HPO4 2 minus. Okay, in this case that means that's 0.092 times 1.3 times 10 to the negative 6 all over 0.341. That's going to equal then 3.507 times 10 to the negative 7. And again, that's Kb. And we know that Kw is equal to Ka times Kb. In this case, then to find Ka, we move Kb to the other side. So we say Kw over Kb is equal to Ka. And again, we know what Kw is. That's 1 times 10 to the negative 14. So we want to divide that by 3.507 times 10 to the negative 7. That should get us a Ka value of 2.85 times 10 to the negative 8. Okay, so let's start with the second type of problem we're going to see in this unit, and that's calculating pH. Okay, this is going to differ because we want to use an ice box here. So we're going to want to use ice box. So let's do a sample problem and see how it goes. So let's say we have a solution of formic acid. So this is HCO2H, that's formic acid, plus water. That's going to be in equilibrium with H3O plus HCO2 minus. The Ka value here is 1.8 times 10 to the negative 4. Okay. The initial for our formic acid is going to be 0.534 molar. So I want you to give this video a pause and see if you can figure out how to calculate the pH. Okay, so again, we want to do an icebox, right? So this is our initial. We have some change, and then we have some value equilibrium. So our problem, we have no initials here. And of course, water we can cancel out. The change is unknown. So we can call that minus x. That would be plus x plus x. And of course, that comes from our balanced chemical equation, right? If there had been a 2 here, so if there had been, let's say, a 2 here, then this would be then 2x. But in this case, there's not. So we can ignore the 2. Okay, so now let's look at our equilibrium values. So it'd be 0.534 minus x. This one would be plus x plus x. So we simply add our initial and our change together. Let's put this into our equilibrium expression. We know that Ka has to be the products over reactants. So in this case, x times x over 0.534 minus x. You might be wondering, how do we solve this? It looks kind of hard to solve. This looks like some math maybe you're unfamiliar with. Well, let's look at our Ka value. We discussed that if K is much smaller than 1, it's a weak acid. So this case is a weak acid. And typically, when Ka is much smaller than 1, we can typically ignore the change in our initial. What that means for us is that whatever change happens here, that's still going to give us something around 5.34. So what that means is we can plug this in here, and we can solve. So let me bring this down a little bit here. Okay, we know that Ka was 1.8 times 10 to the negative 4. That's equal to x times x over 0.543. So now let's solve. Move this to this side. So it'd be 0.543 times 1.8 times 10 to the negative 4 equals to x squared. So we're going to take the square root on both sides. Okay, so doing all this should result in an x value of 0.00980. And if you scroll back up here, what we see here is that our x value is our equilibrium value of H3O plus, or our H plus, which means that the negative log of our x value, so 0.00980, is equal to our pH, which means our pH is equal to 2.008. But you might be asking, well, we made an assumption here, right? We made this assumption here that this would be okay, but how do we prove that it is actually okay for us to make that claim? Well, what we can say is that if our x value divided by our initial value for our acid, if that is going to be greater than 5%, we cannot approximate. So we cannot approx. But as long as x over 0.534 is less than 5%, it's okay. Okay to approx. So let's apply it here. We know our x value is 0.00980 divided by 0.543. And to get a percent, we have to multiply by 100. So multiply by 100, we get 1.8. And that's going to be less than 5%. So we know that it's okay for us to approximate. So let's say we have another problem here. Let's say we have NH3 plus water, and that's going to be in equilibrium with NH4 plus OH minus. Let's also say that our Ka value is 1.76 times 10 to the negative 5. And lastly, let's say we have initial starting concentration of 0.0325. The question here is, what is our pH? Pause the video and see if you can solve this problem. Okay, so let's start this problem. First thing you might notice is that we have Ka here, but if you look at our problem here, NH3 is actually a base. So first thing we need to do is actually calculate Kb. So we know that Kw is equal to Ka times Kb. So knowing that Kw is 1 times 10 to the negative 14, we can divide by Ka and get our Kb value. And that's going to be 5.68 times 10 to the negative 10. Okay, so now we can solve this problem kind of like normal. So we create our icebox. So kind of congested here on a little bit of space, but we'll make it small. We don't have to worry about our water. We have 0, 0. We have some change here. We're going to add that change here and here. And again, the molar ratio between these is all 1 to 1, so we don't have to worry about multiplying x by anything. So equilibrium then is 0.0325 minus x, plus x here, and another plus x. So again, then our Kb expression has to be these two x's multiplied. That's going to give x squared, divided by whatever our reactants have, so that's 0.0325 minus x. And again, we can do the same approximation, and we'll check out later. So we can say that this part right here is equal, or is about equal, 0.0325, which means that our Kb is equal to x squared over 0.0325. Knowing that Kb is here, we can plug that in to here and solve for x. So again, we're going to say here that 5.68 times 10 to the negative 10 is equal to x squared over 0.0325, which means 0.0325 times Kb. I'm going to call it Kb, I'm running out of a little space. All that square rooted is equal to x. So now let's solve for x. I'm going to scroll down here. x is equal to 4.29 times 10 to the negative 6. And if you look back up to our icebox, well, x has to be the amount of OH minus we have remaining, which means that our OH minus concentration is equal to 4.29 times 10 to the negative 6. And if you remember from the very beginning of this video, we talked about different ways we can get pH, knowing pOH and the concentration of OH. So we can use any way there. I want to use that 14 minus pOH is equal to pH. So I'm going to take 14 minus the negative log of 4.29 times 10 to the negative 6. And we know that's going to be pH. So plugging all that in, we should get 14 minus 5.36. And that's going to be equal to 8.63. Okay, so let's talk about the very last type of problem that we're going to be seeing here with acid and base. And that's going to be buffer problems. Problems where we have a buffer. And kind of just make it simple here, when we have a buffer, it's the same thing as saying that we have a common ion. And if you remember what happened in common ion, we're pretty much going to have more than one initial concentration in our icebox. Okay, so it'd be very similar to how we did it in solubility, but now we're talking about acid and bases. So let's give an example here. As typically for these type of problems, it'd be a little wordy, but typically we'll say, okay, we first added sodium acetate, that's going to be NaCH3, CO2, into water, and that's going to create sodium ions plus acetate. And let's say now we're going to add this solution with regular acetate, which is CH3, CO2 in water. And essentially, what's going to happen here is this sodium is a spectator, so we can ignore this. So essentially what this becomes here is this type of problem, where we have here common ions here, our acetates, and now we need to figure out something about it. So maybe the K value, K is equal to 1.8 times 10 to the negative 5. Let me use some initial concentrations here. So this is 0.1 molar, 0.1 molar. I want you to find the pH. So pause the video and see if you can determine what the pH is going to be. Okay, so I scroll down a little bit here to give me some more space. But it's going to be essentially the same thing that we've been doing. This is minus x, water we can ignore, plus x on this side, plus x on this side. So then at equilibrium, we would say this is 0.1 minus x, 0.1 plus x, and this one's also x. So when we go to write a K expression, we know that has to be over acetate with the negative charge, H plus, all over concentration of acetate. So we can plug in our values here. So 1.1 plus x times x all over 0.1 minus x. If we say that x is really, really small, we can ignore x when we're subtracting it from 0.1. What that gives us then is 0.1 times x all over 0.1, which means our 0.1 cancels out. So x is equal to k, which means that x is equal to 1.8 times 10 to the negative 5. X is also the value of H plus, which means simply negative log 1.8 times 10 to the negative 5. That's going to give us a pH of 4.74. Yeah, so we're going to encounter problems here. We're going to add acids or bases and see how our buffer changes. So let's first start off with adding some sodium hydroxide. So let me rewrite the problem. So let me rewrite the problem here. CH3, CO2H plus water. We know that breaks down the same way. Let's just say we have the same things here, 0.1 molar, with K still being 1.8 times 10 to the negative 5. But let's say I added. So let's say I added here 0.1 molar at 1 milliliter. So 1 milliliter of 0.1 molar NaOH. How would that affect our problem? So whenever we have things like this, we know that the NaOH will dissolve completely. Dissolve complete. Which means that we will have 0.1 molar times 1 over 1,000 liters of OH minus. So what we have to determine here is how is this going to impact our equilibrium? If we add acid, in our case here, is it going to affect our products or is it going to affect our reactants? Well, to think about it, we have to consider which side acts like an acid. Is our reactant side the acid or is our product side the acid? What we see here, we lost the H here to go from here to here. And going this way here, we have to gain the H. So if this side acts like an acid, this side like a base, our base is going to react then with our acid. So CH3, CO2, H acts like our acid, react it with our base, and we're going to create here the acetate anion plus water. And so now this becomes a limiting reagent problem. So this is a limiting reagent problem, or limiting reactant too, if you want to call it that. So we have to determine which is a limiting reagent and determine then what our end concentration of CH3CO2 is and what our concentration of CH3CO2H would be. Okay, so if you remember your limiting reactants, right, you want to get everything in moles, see which one is the limiting one, and we can go from there. And so what we can say is, well, we know the moles of OH is what we did right here. That's going to give us 1 times 10 to the negative 5. Let's assume, actually going to give you this information, but let's assume that we have this solution to be a volume of 100 milliliters. So then we would have to do here 0.1 times 0.1. That gives 0.01. That's how many moles we have here. So clearly our limiting is going to be our OH minus. So now we determine how much CH3CO2 we create. If you remember here, we already started off with a concentration of 0.1. And if you want to convert it to moles, then it would be 0.01. So that means that we have to subtract from both sides here. 1 times 10 to the negative. On this side, we're going to add it. So then we should get 0.00999 here. Then we'll get 0.01001. Okay, so we got moles, but now we need to calculate the molarity again. And you might be wondering, well, okay, let me just divide both these by 0.1. We should be good. The issue is here, though, we actually have a new volume, right? We added 100 mils into 1 mil. So that means our new volume is 101. So if I move this down a little bit here, we can get that our new molarity is going to be 0.00999 divided by 0.101. Same thing here, where molarity is equal to 0.01001 over 0.101 to get our new moles. So we have this one to be 0.098. This one's going to be 0.0991. Okay, so now we go back to original expression, plug these in for our initial, and then we're going to solve for what our pH is going to be after we added 1 milliliter of 0.1 molar solution of NaOH. Okay, so I rewrote the problem here. And so now we want to find the pH, right? So same idea here, minus x plus x plus x. And of course, the initial amount of H plus is 0. Same thing here, 0.098 minus x. This one will be 0.099 plus x. Here we also have plus x. We know the K expression from before, so we know it's going to be our products multiplied together over our reactants. In this case, just reactant. Again, we can ignore our subtracted by and added by x because we're saying x is very, very small. And so now let's figure out what x is going to be here. We can simplify and say K has to be this. And now we can substitute in our value of K. So 1.8 times 10 to the negative 5 is equal to all of this. We're going to do some algebra here and rearrange the expression. We're going to multiply by our denominator and then divide by our numerator. So we're going to get here that 1.8 times 10 to the negative 5 times 0.098 divided by 0.099 is equal to x. That makes x equal to will be 1.7 times 10 to the negative 5. And so to take the negative log of that, so that will give us our pH, which means our pH is 4.749. So you remember from before, our pH, let me scroll down a little bit here. Our before pH was equal to 4.744. I didn't put the extra digit down here, but for now it matters. And you see how we changed by a very small margin, right? We went from this 0.744 to 0.749. And that's pretty characteristic of our buffer, right? We shouldn't expect a very high pH change. So that's how we deal with any buffers here. If you go back to how we did the problem, we're always going to start with first determining how much of our common ion we have remaining. So we react either our acid or our base with our expression's acid or base to determine what's remaining and how much is remaining. And then from there, if you go back down, we get what our icebox is. Okay? So the last thing is kind of more conceptual thing, but I wanted to talk about polyprotic acids. Okay, so there's one more thing we got to cover. This is more of a conceptual thing here, but it's the idea of polyprotic acids. And so we can really break down this word: protic, proton, poly, more than one. So polyprotic acids are acids that give off more than one proton. And so most of the time we will be talked about monoprotic. So put that in white here, monoprotic. That's when you're giving one proton, right? That's going to be your HCl, the one we just talked about, acetate, right? You can only give off one proton. But sometimes there's going to be some problems with this polyprotic or even diprotic, right? That's more than one. So how do we determine which version of that acid is stronger? So let's give an example here. Okay, so let's say we have H2CO3 plus water, and we know that's going to be in equilibrium BHCO3 minus plus H3O plus. And you see here we have another hydrogen to lose here, another proton to lose. So we can say this is HCO3 minus plus water, and that turns into CO3 minus, 2 minus plus another H3O plus. So there's a pretty quintessential here polyprotic acid. how do we determine then which version is stronger? Let me read the k values here. So k is equal to here in the first one, k1, 4.3 times 10 to the negative 7. For k2 here, it's going to be 4.7 times 10 to the negative 11. So we already know from the k expression which one is a stronger acid. We know this one, stronger acid, it's closer to 1. So this one has to be a stronger acid. Not a strong acid, but a stronger acid. So then how do we determine if we had to do a problem? What would be the pH of the solution? What we'd have to do here is first see what the major kind of provider or the major giver of protons in the solution is. And so what we can say is that if Ka is bigger than 20 times K2, and remember we have to make it so that K2 has to be the lower K value. If this is true, then Ka, so if this is true, if true, the dominant H plus giver is only K1, therefore ignore K2. So essentially, we can just do one icebox with our equilibrium, and the chemical equation given by it. So let's see here. Let's do 20 times K2 and see what we get. So we get 4.9 times 10 to the negative 10. And we know that has to be way less than 4.3 times 10 to the negative 7. Negative 7 is much bigger than negative 10. And again, from here, if you wanted to, if we're given some concentration, we could find the pH of the solution. But we already been doing that a lot, and we're going to call the video here. So if you guys learned something, if you guys appreciated the content, please do give a like. Comment as well if you want to see another video of more problems like this or any other topic you wanted to cover.